Section 3.4, concavity and the second derivative test is what we are going to discuss. Okay, definition of concavity says let f be differentiable on an open interval I. The graph of f is concave up on I when the first derivative is increasing and concave down when the first derivative is decreasing. Okay, and so you're looking at the slope of the slope essentially. So if you think about it, when a function itself is increasing, decreasing, we look at the first derivative. If we're looking at when the first derivative is increasing, that means we're looking at the second derivative, it's the slope of the slope. So we will be looking at where this happens is where this is positive. And where this happens is where this is negative. Okay. So we can test for concavity because, again, it's what I said. If f double prime is greater than 0, then it's concave up, okay? And then if it's f double prime is less than 0, then it'll be concave down. All right. So first example we're going to do is we're going to determine the open intervals on which the graph of the function is concave up and concave down. In order to do this, we're going to be looking for the second derivative. So in order to do that, we have to look at the first derivative. So f prime of x, we're going to be looking at the derivative of e to the negative x squared over 2. So we'll do e to the negative x squared over 2. You have to chain rule this times the derivative of negative x squared over 2. Keep in mind that this is the same thing as this. So when I do the chain rule and I do the derivative of that exponent, I'll have 2 times negative 1/2, which is negative 1. So I'll just have negative x. Okay? And then I'll simplify that a little bit. So I have negative x e to the negative x squared over 2. Then f double prime of x is equal to, we're going to have to product rule it. So 1 and 2. Okay, so we'll do our 1 d2, and we already know the derivative of d2. That is exactly the function we derived earlier. And so it is, the derivative of 2 is actually this whole thing that we've been working with. And so I will have 1 d2. So the derivative of the second part is this plus 2 d1, which is just negative 1. Simplify a little bit. We have negative negative, so we'll have x squared e to the negative x squared over 2 minus, because the negative 1, e to the negative x squared over 2. They each have an x squared over 2, so in order to, we're looking for positive and negative, so in order to do that, we need to know where it's 0, so when we can know, like, to the left of this value, it's below 0, and to the right of this value, it's above 0, or something along those lines. So we're going to go ahead and factor that out so that we have x squared minus 1. Okay, we need to figure out where it's equal to 0, so we can put numbers on a number line, just like we did with increasing and decreasing. Again, you're finding increasing, decreasing of the first derivative. So the rules still apply. It just means concavity, concave up, concave down. Concave up means it can hold water. Concave down means it can't. Okay, and so when we solve this, you'll use the zero product property, which means I'll set this equal to 0, which is awesome because unless there's addition or subtraction outside of the function, meaning big and not in the exponent, added or subtracted, exponential functions can't be 0, but this can be 0. And I can add 1 to both sides and square root both sides. And when I square root both sides, I get plus and minus, so I get x is positive and negative 1. So those are the zeros I put on my number line. Okay. And this is for f double prime. And I need to pick a value to the left, a value in between, and a value to the right. Okay, and those belong on that interval. There's no endpoint, so we don't have to worry about keeping it within there. You can pick any value to the left, negative 1. If you want to pick negative 100, go for it. And you're going to plug in those values into the derivative. So we're going to plug it in here. Keep in mind, this term here is always positive, so it's not going to affect sign. So really, the only thing affecting the sign, positive or negative, is the x squared minus 1. Okay, even though that e has a negative exponent, that's just going to make it a smaller value, not a negative value. It would have to be negative in itself. So I plug in -2, I get 4 minus 1, so that's positive. And I do it this way. I make positive and a happy face because it's happy. And that shows me it's concave up. On that, it holds water. So here's your up. This is what down looks like. Think down is in sad. Okay, if I plug in 0, I get 0 minus 1, so it's sad. And I get plug in 2, and I get 4 minus 1, which is 3, and it's positive. Okay, so I have concavity, so I'll say concave up from negative infinity to -1 and 1 to infinity. So this interval here was up, and this interval here is up. It is concave down from -1 to 1. So that would be the answer to that problem. Same instructions, just a different problem. We're going to determine the open intervals on which this function is concave up, concave down. It is going to be a little bit of a harder derivative because you notice it is a quotient starting off. Okay. So we will do f prime of x, and we will do low d high minus high d low all over the square of what's below. And we do need to simplify it. Okay, so we will have 2x cubed minus 8x minus 2x cubed minus 2x all over. And let's leave this here because when we do this derivative, we can chain rule it. Okay, and that will leave us with negative 10x. So that wasn't too bad. So now when we do our second derivative, because we are doing concavity, we'll do low d high of this function here. So we will do low d high minus high d low, and I have chain rule, so it's going to be 2x squared minus 4 with an exponent of 1. I'm not going to write it. And then times the derivative inside, which is just 2x. Okay, all over the bottom squared, which will now be to the fourth power. You don't have to write squared, squared. You can just do the fourth power. Okay, so we'll go simplify a little bit. We can do, we'll need to FOIL x squared minus 4. So that'll be x to the fourth minus 8x squared plus 16 times -10 still. And then I'm going to do this plus 10x there on the outside and simplify this to distributing this 2 and this 2x. I will have 4x cubed minus 16x. I'm going to keep the bottom as is for now. Okay, equals. All right, let's simplify the top. They both have a 10, so I really think it'd probably be easiest if we just factored out a -10. I think that would be pretty easy to do. So we can do -10 and x to the fourth minus 8x squared plus 16, and then minus x minus 4, x to the fourth minus, and that'll be a change your sign because you factored out a -10, so you have to multiply by -10 to make that positive, 16x squared. So we have this craziness. And hopefully I don't run out of space. If I do, I'll start erasing. All over x squared minus 4 to the fourth. All right, let's combine like terms in the numerator so that I have my -10 and I have -3x to the fourth and positive 8x squared plus 16 all over x squared minus 4 to the fourth power. Okay, so then when we are looking at this, we need to look at how it factors. Okay, and the numerator does factor. You can think of this just like a problem like an x squared. Imagine this as negative 3x squared plus 8x plus 16, like a typical quadratic. And you could factor it by using guess and check method, or if you know the four-step method, you can do that. If you're not up on factoring, make sure you study that. I do the four-step method, so I'm going to look at multiplying negative 3 and 16 and getting negative 48 and seeing what multiplies to 48 and adds to 8, and then it will factor by grouping. When I do that, I will get x squared minus 4, which should look familiar, okay? And I will also get negative 3x squared minus 4. And I have an x squared minus 4 to the fourth. So we can actually get rid of that. There's going to be that. And we probably could have factored that out earlier on, probably up here, because they all have one. But it works at the end too. And so what I know, though, is when I do my number line, I have to pick values that make the derivative undefined, but are defined here. We have to test around places like that. And then also I need to figure out what makes the actual function equal to 0. Okay. And so I would use a zero product. Where the top is equal to 0 is going to be where this is equal to 0. So if I add 4 to both sides, divide, I'm going to have x squared equals negative 4/3, and I can't square root, so that doesn't give me anything. The bottom, though, if I solve the bottom, will show me x can't be 2 or negative 2. And if you look at the original function, that works with that domain. X can't be 2 or negative 2 there either. And so I'll do negative 2 and 2, and I'll pick some values to test around. Okay. And I'm going to plug them into where would be the best place to test for. I think I'll plug them in here, okay, to figure out whether things are going to be positive or negative, okay. Keep in mind that negative 10 out front has something to do with that. Okay. I'll actually make it a little easier. I'm going to distribute the negative through this so that I only have to worry about positives. Okay, so the 10 will now have no effect. So I'll plug in negative 3, and when I square any negative number, it's positive. So if you look, this will always be positive, so the top doesn't control the sign, the bottom will this time. So negative 3 squared is 9. 9 minus 4 is a positive number, so it's going to be concave up. And it is cubed here, but that won't affect sign because it's an odd power. I'll plug in 0, and 0 minus 4 is negative 4. And then I'll plug in 3, and I get 9 minus 4, which is 5. Okay. You can plug it into the whole thing. As a reminder, we did that when we did increasing, decreasing, but you don't have to plug it into the whole thing. You can just do it in parts. All right, so we have concave up from negative infinity to negative 2 and 2 to infinity. And then we have concave down from negative 2 to 2. So that's that answer. Okay, we're going to talk about point of inflection real quick. Okay, a point of inflection is when the concavity changes. Okay, is a key point of that. So where it goes from happy to sad or sad to happy. So you can kind of see where this was concave up and then it changed from concave down. This would be a point of inflection. This is a point of inflection. Here's another example of point of inflection. So you can see where it's changed from where it could possibly hold water to not. Okay. Points of inflection happen where this happens or where it doesn't exist. In order for it not to exist, though, it does have to exist in the actual function. Okay? So, for example, we wouldn't actually have points of inflection at 2 and negative 2, even though they were points we found, because they don't exist in the original function. But we would have points of inflection at negative 1 and 1 because negative 1 and 1 do exist here. So make sure they exist in the original function, which you would quickly find out because you get ordered pairs. You have to plug it into the original function. Okay. So determine all the points of inflection and discuss the concavity of the graph. So we're doing what we were doing, but we're just adding on the points of inflection. So we still need to do our first derivative, 4x cubed minus 12x squared. And then we need to do our second derivative. And we'll get 12x squared minus 24x. And we need to figure out where it's going to change. And so we will factor this. I'm going to factor out 12x. And it'll leave me with x minus 2 equals 0. So I'll get x equals 0 and x equals 2. And I will put those on my number line, 0, 2. You need some test values, so I'll choose -1, 1, and 3 in between them. And I'll plug those in. I'm going to plug them into the factored form because it'll be easy to tell sign. So if I plug in -1, I'll get 12 times -1, which is a negative. And I'll plug in -1 minus 2, which is a negative. And a negative times a negative is a positive. So here, I plug in 1. 12 times 1 is positive, but 1 minus 2 is negative. I will plug in 3. And 12 times 3 is positive. And 3 minus 2 is positive. Okay, so we will have concave up from -infinity to -1. Remember that these are just test points, so don't do what I just did. Make a mistake. It has to go to the actual zeros here. Okay, and then it's also concave up from 2 to infinity because you can pick any value. I could have chose -1 million if I wanted to, so it can't be one of your parts of your interval. And then down will be between 0 and 2. It also wanted points of inflection. Okay, so we call them points of inflection. Okay, and those will happen at the ordered pair 0, comma something and 2, comma something. Okay, and those have to go into your original function. Okay, these are ordered pairs actually located on your graph. So when you're doing your actual points, the keyword being points, it means it exists on your function. So you have to plug them in there. So I'm plugging in 0 and I'll get 0. And I'll plug in 2, and 2 to the 4th power is 2, 4, 8, 16. And then we will do 16, it'll be 8. 8 times 4 is 32. So -16. So those are your answers for that. So we did the first derivative test, and the first derivative test was a way to tell max and min using the first derivative, where we showed if it was increasing to the left and decreasing to the right, you'd have a max, and vice versa, you'd have a min. So this is a way to use a second derivative to tell for max and min. So if your second derivative is greater than 0, which means that it looks like this, you're going to have some sort of minimum. Okay, so you'll have a low point here. If you have it greater than 0, it's not holding water, it's down, you're going to end up with a maximum. So I feel like that's a really logical way to think about that. Okay, and then here is the example of that, where you can see where it's going to be happy here and sad here. And you would have a max when it's sad and a min. So this is for the second derivative. So find the relative extrema, and that means max and min of this function here. So we're doing the second derivative test. So I will do f of x equals f prime of x, and we have to do the first derivative to get the second derivative. So I'll do -15 x to the 4th plus 15 x squared. And then I will do the second derivative, and I will have -60 x cubed plus 30 x. And I will factor this because I need to figure out where it's 0. And I will factor out, how about -30x? And I'll be left with 2x squared minus 1 equal to 0. Okay, and so then I'll get x is equal to 0 here with the 30x. And then I will be left with, if you add 1 to both sides and you square root, I'll be left with positive and negative. It's root 1 over 2, but you'd need to rationalize it. So it's root 2 over 2. And those are going to be, and I don't have to do a test value for that. I'm not plugging them in to a test value. I'm going to plug them in to the original function. These are where it's going from max to min. So it's going to be that. So we'll go ahead and look at our where they're greater than 0 or less than 0. Okay, at certain given values. Okay, actually back that up. We don't need this information. That would be if we're doing increase or concavity, but we're just going to use our second derivative. So we do need those. We need values to plug into the second derivative because the theorem says that the value, the actual order pair, is some value that makes it positive or some value that makes it negative. Okay, so those values have to be at critical values, which come from here. So we will solve this. So let's factor out negative 15x squared, and I will have x squared minus 1 equals 0. And so I'll have x equals 0 and negative 1 and 1. And then I plug those in here. And if they are positive, then I'm going to have a minimum. And if they are negative, then I'm going to have a maximum at those values. Okay, so we will have f double prime of negative 1, f double prime of 0, and f double prime of 1. All right, and I will plug in, and you're just looking at positive and negative. So again, I really don't need these actual values. I just need to know if it's positive or negative. So I will plug in negative 1, and negative 60 times negative 1 cubed is a negative times a negative, which is positive. And then I'll plug in negative 1 to the 30, which is minus. And so negative 60 is negative times positive is greater than what will be when I plug in get negative 30. And so this will be positive. Okay, if you want to get the actual value, you can. If I plug in 0, I'm going to get 0. Okay, so that doesn't help us with that. And then if I plug in 1, I'm going to get negative 60 plus 30. So it's going to be negative. So positive, I'm going to have a min at negative 1 comma something and a max at 1 comma something. And that is that second derivative test tells us when your second derivative is positive, you're going to have a minimum. When your second derivative is negative, you're going to have a maximum. Okay, to get those actual order pairs, we just plug them in here. Okay, always plug into the original to get an actual location. So if I plug in negative 1, I will have 3 minus 5, so negative 2. If I plug in 1, I will have positive 2. Okay, so second derivative test, you'll do the first derivative. You'll need to solve it to get your critical points. And then you'll do your second derivative, and that's where you plug it in to see if it's a max or a min.